Welcome back. We have seen in the previous part of the exercise that we have been able to get very performant architecture for our Smith-Waterman algorithm. However, we are not able to get the full potentiality of it, as it works only with small datasets. Well then, what can we do to tackle this problem? We have performed a compression on the output data, as we have noticed that actually we had only 4 possible directions to store. This considerably reducing the memory footprint when storing back the results to the DDR. What we did not consider here is that the input of the Smith-Waterman we are considering here are DNA sequences. In DNA sequences, there are only 4 possible values too, as in the output of our architecture. The DNA character can be in fact A, C, G or T. Again, we can compress also our input strings. This compression not only reduces the amount of data that we are moving from the DDR to the FPGA, but also reduces the complexity of the circuit we are trying to implement. Memory partition is a very expensive operation, as once a buffer is completely partitioned in logic, the synthesizer will have to route each possible cell of the partition buffer. Furthermore, in the code we have written so far, each partition cell is 1 byte wide. Therefore, when partitioning buffer composed of hundreds of characters, it is clear that the complexity of the circuit generated by the synthesizer increases drastically. However, compressing the input data, we are able to drastically reduce the complexity of the circuit, as the partition cells are now 2-bit wide. It is very important to know what are the input and outputs of the application, as knowing this kind of information allows the designer to perform specific optimizations on the data. Let's now change our code to reflect what we have said so far. Let's start with AutoHLS from our project tab and let's define our query as an APU in 512 bits wide. Now, we obviously need n elements divided by how many elements I can store in a 512 bits variable, that in this case is equal to 256. We then do the same thing for our database string. Obviously now, we have to change the dimensions of the memcopy too, otherwise we are reading too much from the DDR memory. Okay, let's then change the calculate diagonal function. It is in fact now taking as input 2 APU ints instead of chars, and then we need to change the way we are accessing these 2 variables. Again, we use the range function to select specific bits from our sequences. For the query, we need to access the index divided by num_lm structure at the specific bits specified by the modulo between the index and num_lm multiplied by 2. The same story is valid for the database character, where index is replaced by the specific index of the database. Now, we need to add a specific branch. It is necessary, in fact, to check if the database character we are considering now is one of the fake one we were sending to buffer out corner cases. Using this new architecture, we cannot send fake data, as we have only 4 possible values in our strings. This is not a big deal. By checking the position of the character, we can easily detect the position and force the database to a variable we know that is surely different from the 4 possible varied characters. Now, let's synthesize and see if anything changed. Okay, we have a problem. I actually mistakenly copied the star in the definition of the strings. Let's remove it and synthesize. While the synthesis is being performed, let's take a look at the code. And let's try to understand if we change the operational intensity of our kernel. We are adding some operations to retrieve the correct data from our buffers. Also, the memory traffic is reduced. We are in fact compressing the input sequences too. Our operational intensity moves from around 15 to around 22 in the smaller dataset, worst case scenario, to around 180 in the biggest dataset, again, worst case scenario. It is great that the operational intensity increased again, but now let's see if the synthesizer terminated the hard work. The result of the synthesis is not so satisfactory. Our design, in fact, does not fit on the FPGA device. This is very disappointing. Probably we are not doing our best to specify the architecture we want the synthesizer to create. We need to think of a new way to tackle this problem. We are consuming too many resources. Our systolic array needs to access in parallel at all the elements of the query and at multiple elements from the database. Oh, wait a second. In our code, we are copying entirely the database into our FPGA device, and then we are completely partitioning it. This is not necessary at all. The architecture, for each clock cycle, needs to access all the elements of the query and only n elements from our database. We need to implement a data structure that contains always the n elements of the database that are needed at the specific clock cycle. The data structure we want to implement actually works as a FIFO, and is called shift register. Every clock cycle, the shift register shifts in a new value into the register and removes the element that is on top of it. In this way, we can partition only n elements and keep database of greater dimension. This is awesome. Later on, we will see how to implement the shift register, and we will observe, as increasing the amount of data sent to the FPGA device, the final performance of the system will increase.